Now let us talk about the organization of computers. In this specific topic, we'll be discussing about different members or subsystem of a computing system in general. So this is what the organization study is. Okay, so in this whole semester, what we'll try to explore is computer system as an organization. Just to give an analogy, right? So let's say university is an organization, right? And there are specific members which has specific functionality. There is a dean, there is department chair, there is professor, there are lecturer, there are students, there are student assistants, and non-teaching staff. These are the members of this university organization, and each of them has a specific role to play inside university system, right? Similarly, we'll study computing system in that angle, like what are the major components of a computing system and what is their functionality, what is their role in the computation world or inside a computing system. So that's our target for the entire semester study. In this specific class, in this today, we will try to see those major components, major member of this computing system at a glance. Okay, and then we'll elaborate in successive classes, we'll elaborate on those members. Okay, so as far as we have seen in last couple of slides, a computing system in general, in abstract view, we have a processor, okay, and then there is an associated storage memory, and there are input devices and output devices. Input devices like a keyboard, mouse, output devices like display, printers, those things. Storage and memories, it can be ROM or RAM, they're hardware memories. It can be disk drive, which is also hardware but a different kind of devices there. But in general, they are storage or memory. And these arrows means the direction of the information flows. Okay, this processor, which basically crunches information, compute based on the information, it picks up information from the input devices and sends out information to the output devices, where the relation of the processor memory is a bidirectional. It can send and store information inside memory and retrieve piece of information from stored inside the memory uh, as it needs. So this is a bidirectional relation, right? It can store into the memory, it can read from the memory. So information flows in both way, out of the processor into the memory, out of the memory into the processor. Okay, so from this view, what we can do, let's club this input and output device together and call it as an IO device. Okay, so this IO device, now this class has all these devices together, right? Keyboard, mouse, display, printer, for example. And now you see our information is now become from this block, this conceptual IO device block, as an information is a bidirectional. Inside maybe they're differentiated. All this processor gets input from the subsystem of keyboard, mouse, and then sends out information towards a display printer. That's a different story. Okay, that's a detailed view of that. But in a generic view, IO device has a bidirectional information exchange with the processor, just similar to the storage or the memory, bidirectional exchange of the information. In this picture, I have introduced one more concept called address. So what is this? So there are like many devices, like IO devices, like here at least 4 of them, right? There can be many type of storage memory devices. I have seen like 2 of them here. Now point is that when processor wants to have an information exchange with with a memory or IO device, it need to really specify which specific device is it targeting. Is it targeting to store something in the disk, or is it targeting to store something in the ROM? Is it targeting to get some information from the mouse, or is it targeting to get some information from the keyboard? Or is it targeting to send some data to the display or send some data to the printer? So how a processor distinguish and tell the storage system or IO devices that which specific one to pick up? Okay, and that mechanism is through the address. Address is a number. Each of the device is associated with a unique number, and that number processor specifies. Say for example, let's say disk drive has a number 55. I'm just assigning something very arbitrary here. Okay, so disk drive has 55. Let's say RAM has 95. Okay, so if a processor wants to store information into the disk drive, it will set the address value to 55 and send the information. So the storage system know the information it's getting has to be stored inside the disk drive because processor specify address 55. Whereas if processor would have specified 95, then the storage system is distinguished, hey, this information is targeted for the ROM or RAM system. So this is what the address is, okay, in this picture. So now let's see, can we further simplify this whole view? Okay, so here we are putting in one more information, extra information that's coming out of the processor, which is the IONM. It's tagged as IONM, which essentially means that I am giving an address which is either targeted for an IO class devices or targeted for memory devices. Now let's see the previous picture. Okay, so we have various IO devices, we have various memory devices. Now let's say if we assign a number 55 for the disk drive and number 55 for the display. Okay, and see, in a computing system, though this information path has been sent differently, it is not. Okay, we'll merge them later. Okay, the point is that this processor is sending out an address, and this address is this signal is going. They're not a separate signal, by the way. This is the same signal. I have just shown it in a two separate way, but let's assume they are the same signal, same electrical signal going to both storage and the IO device. And disk drive has been given a number 55 and display also given a number 55. In that case, if a processor produces an address 55, then the question becomes, is it targeted for my disk drive or is it targeted for my display? So to solve this problem, this special signal IONM has been introduced. This is a 1-bit signal, and this one is telling that if the signal value is a logical one, then it's an IO. This address belongs to or targeted to the IO device. If it is 0, then it is targeted to the memory device. Okay, so this is a 1-bit value, 1 or 0. Can assume a value 1 and 0. If it is 1, it is this address targets to the IO device. If it is 0, it's targeted to the memory. So that means in this example, let's say my disk drive has assigned 55 value and display also assigned 55 value. So processor producing value 55 on the address line, okay, and to give it to the memory, it set this IONM value to 0. So which essentially means to the memory system is that, hey, this guy is 0, so I need to take this address and send it to the disk drive. Now, if it has been set to 1, then what would happen? Memory subsystem would say, oh, this is 1, which is not for me. I even don't want to look at this address. Okay, I'll skip it. Whereas the IO device system, that will say, hey, this is 1, so this is targeted for me. Okay, I got a address 55, so it must be targeted to the display. So I'll send the given information to the display. So this is how this IONM signal works. Now, why this IONM signal was introduced separately than address? Why not? It's a part of the address itself. Like, means, for example, why not we just given number 56, right? Instead of both assigning your disk drive and a display assigning a value or assigning a number or assigning an address 55, why don't we have just assign 55 to disk drive and 56 to display? Okay. The reason is that in older days, number of bits available was very limited. Okay. So this address, there could be only minimum set of numbers. It cannot be infinite. Okay. Less number of bits, like 8-bit, earlier it used to be the 8-bit computing system. With the 8-bit, you can only specify 256 values. Okay, only, so that means you are limited to that number of devices. Okay, so they want to increase the space. Instead of having in IO devices and memory devices together as a 256 different devices, they want to increase the scope so that both memory can have different 256 different devices, and IO also can have 256 different IOs can be associated with the processor, giving a total device number of 512. They introduced this one single bit, okay, along with the 8-bit address. So that's the origination of this, and this type of strategy is called as an IO mapped IO. Okay, because of a separate IO control signal is used, it's called an IO mapped IO. And the reason for it is that number of availability of the bits in a system. It used to be very low power computing. Its number of bits, available bits to represent value was less, like 8-bit, 16-bit was at most and stuff like that. That's why this IO mapped IO strategy was developed. Now, as we advanced in the technology, we have now 64-bit computer, which means theoretically we have 64-bit to make up an address. That's too much. Okay, that's too much. So that's when a strategy was developed to actually make this IO signal into as a part of the address itself. Okay, so it's saying that, okay, I have these numbers like values, all the set of values represented by 64-bit, and I have this IONM signal as a part of that address. Okay, so now all the modern computing system doesn't have a separate IO signal, IO identification signal, and this strategy is called a memory mapped IO. Essentially, it means that your IO devices are also treated as a memory device from processor perspective. So when a processor look at a system to its everything is a memory. Okay, only a part of the system is only a part of the system is the memory part of the memory system is connected to your IO devices. Okay, only the part of a memory system is connected to the IO devices, rest of them is connected to the memory storage devices. So all modern computing system has this very simplistic view of information exchange. From a processor perspective, it produces an address. That address may belongs to sometimes to the IO default IO device. That address can denote part of the memory storage itself, like a disk drive system, like an ROM, like an RAM, all the hardware memories, etc., etc. But in a nutshell, processor is nothing but a memory. Everything is memory. Everything processor produce an address upon to which it needs to exchange information. Either it needs to write into the memory or read from the memory. So this is the first simplistic view that will be starting in more: a memory system and a processor. Two major members of a computing system in a modern computing system: a processor and a memory.